Imagine a typical Thursday afternoon where every major communication grid, transportation network, and global financial market freezes simultaneously. At the localized level, critical infrastructure shuts down, hospital ventilators power off, and precision medical equipment, like the monitoring loops inside modern pacemakers, simply stop registering heartbeats. This systemic failure follows the sudden disappearance of a single entry on the periodic table, element 14, silicon. This handful of coarse, light-colored sand and pebbles shows the element in its natural form. You are looking at the raw state of the second most abundant element in the Earth's crust. This creates a paradox. The global systems we've built rely on the dirt beneath our feet. We are left with the question of how ordinary sand was ever coaxed into performing complex digital logic. Chemists first isolated silicon in the early 19th century, naming it after the Latin word silex, meaning flint. Despite its abundance, it presents an immediate physical hurdle. Silicon bonds eagerly with oxygen, meaning it almost never appears in its pure state in nature. This 3D atomic lattice shows pure silicon in its natural state. The electrons are tightly bound to the structure, acting as an insulator. But silicon is a semiconductor, sitting perfectly between a copper conductor and a rubber insulator. Apply heat or electrical charge, and behavior changes. Knock an electron free, and electricity flows. Remove the charge, flow stops. Off, on, 0, 1. That invisible atomic switching is the exact physical mechanism behind all modern computer programming. To harness that property, engineers developed an intense, high-temperature industrial process to strip the oxygen from quartz. Melting the material creates an ultra-pure silicon ingot. These dark, reflective silicon wafers, organized in a white plastic carrier, are the result. Sliced from the ingot, they provide a smooth, semiconductor-grade canvas. This photograph captures 3 men examining an early laboratory instrument. They are testing the transistor, the device that first let engineers control silicon's atomic properties. Carving microscopic pathways onto pure wafers scaled the transistor into the integrated circuit. This microprocessor chip, with its gold-plated pins, contains billions of microscopic switches. Mastering this physical manipulation birthed Silicon Valley, where purified rock became the vessel for the world's most complex computing engines. Today, millions of these chips are networked together. These sleek, tall server racks, bathed in blue lighting along a data center corridor, act as the massive, centralized brain of the Internet. The element also scales up to capture renewable energy. This high-angle aerial view of a massive solar farm in a desert landscape reveals rows of silicon panels converting sunlight into grid power. Beyond electronics, it remains a foundational material in heavy manufacturing. This industrial line relies on silicon compounds to form the glowing, red-hot glass bottles moving past mechanical arms, just as it does for modern concrete. But creating these flawless components exacts a heavy toll. A single semiconductor fabrication plant requires millions of gallons of ultra-pure water daily, alongside toxic chemical solvents and immense volumes of raw electrical energy. Our demand for this purified element is now colliding with the limits of Earth's resources, forcing an urgent search for sustainable manufacturing practices. The immediate future relies on expanding this physical hardware. Training artificial intelligence and running complex neural networks requires processing power that only next-generation silicon chips can provide. The element physically integrates into our transportation. Here, in a modern assembly environment, this electric vehicle chassis exposes a complex battery pack and drivetrain, systems managed by embedded silicon sensors. It sustains human life directly in clinical settings. This piece of white medical equipment, with its dials, tubes, and monitors, relies on silicon microprocessors to deliver precision, automated patient care. Look closely at this single grain of quartz sand catching a solitary beam of light. Contrast our high-tech achievements with this raw, chaotic material. Humanity took the dirt beneath its feet, rearranged its atoms, and built the logic that defines the modern age.